We've been talking about eigenvalues and eigenvectors, and it's good to have some intuition for them. So we can ask a simple question, some example related to an example. Consider that you live in 3 dimensions, as you do, and the operator is going to be an operator that takes vectors in this 3-dimensional space and rotates them. It's a rotation operator. That's the linear operator. That's the T we're considering. And we want to know what are its eigenvalues and eigenvectors. So what is the vector space? 3-dimensional real vector space. What is the operator? Well, a rotation. So let's be even more explicit. Take the x, y, and z axis and consider a rotation around the z axis. Okay. So that is physically what happens to the vectors in the vector space. They're rotated around the z-axis. So what are the vectors that are left invariant by this rotation? Well, that's the eigenvectors. Are there eigenvectors that are left invariant? Well, any vector that is not along the z-axis, say the z-axis is vertical, will be rotated. So a vector in the x direction will be rotated, a vector in the y direction will be rotated, a vector in an arbitrary direction will be rotated, but a vector in the z direction is not rotated, is left invariant. In fact, its length is not changed. So for a rotation operator, for a rotation, if the vector space is R3 and T is a rotation about the z-axis, we've discovered that there's just one eigenvector. Is the vector along the z direction, or the span. Well, it's one eigenvector is a vector along the z direction. The set of all those eigenvectors is the span of that. So there is a lambda equal 1, because that vector is not affected by the rotation, so it's just left totally invariant. And the vector is any vector in the span of the vector z hat. So this is an operator, and we got for it one eigenvector and its eigenvalue. And you may say, well, there's not too many. Are there more? No, there are no more eigenvectors, no more vectors that are just left invariant up to a scale. So you could wonder, and maybe it even might sound wrong to you what I'm saying here, and may sound wrong because if you've calculated eigenvectors and eigenvalues, you would think, no, I'm going to find 3. But the fact is that you would find things with complex coefficients. And if this is a real vector space, as we said it is, there's just one eigenvector. If you take another example, V equals R2, the plane, and T, a rotation again. Now you have just the plane, the xy plane, say, and you're rotating vectors rigidly. Well, then there's just no vector that is invariant. Nothing is invariant. No non-trivial vector is left invariant by a rotation, so no eigenvectors nor eigenvalues. So real vector spaces have this complication. They sometimes have very few eigenvectors and very few eigenvalues. So this is one reason we are interested in going to complex vector spaces. In complex vector spaces, things will be more interesting. There will always be at least one eigenvalue, which is progress, and many times for nice operators there will be many eigenvalues and many eigenvectors, as we will see. And by restricting ourselves to special kind of operators in complex vector spaces, we will get things for which the eigenvalues tend to be real, and the eigenvectors can be used as physical representations of our states. So basically, these two examples are a motivation to examine complex vector spaces. All right, so if we get more eigenvectors, what happens? Now, the one piece of intuition that is very nice to have is that if you have eigenvectors for different eigenvalues, these eigenvectors tend to be linearly independent. So you have a set of eigenvalues that you found and the corresponding eigenvectors. If the eigenvalues are different, the eigenvectors are linearly independent. This theorem will even be made stronger soon in this course, where we will show that for certain operators, these eigenvectors are in fact orthogonal. But at this moment, we cannot speak of orthogonality. We have not defined an inner product on the space. It's something we've just constructed vector spaces and put the least structure on them. There's just the addition of vectors and multiplication by numbers. With that already, we've made a lot of progress and have understood the existence of operators and some of their properties, but there's still more structure to be added, as we will do soon. So at this moment, I want to discuss this thing of the linearly independent. So I want to use this theorem, consider this theorem. So theorem. Consider a T belonging to L of V, and let lambda 1, lambda 2, up to lambda n be distinct eigenvalues and u1, u2 up to un, the corresponding non-zero eigenvectors. Then this u1 up to un are linearly independent. That's it. That's the theorem we want to discuss. So again, you get one operator, you compute the eigenvalues, or you find a set of eigenvalues, and suppose they are distinct. Find eigenvectors. These are the eigenvectors, and they are non-zero. The claim is that these eigenvectors are already a set of vectors that are linearly independent. There are no linear relations between them. They can help you span the space in particular, which is very useful. So there's a few remarks that we can talk about here. First, again, since we don't have an inner product, we cannot discuss whether these vectors are orthogonal to each other or something more explicit. It's just they're not linearly independent. You're getting new things. Now, the other question is, sometimes we've said it could happen that for a given eigenvalue, you would obtain more than one eigenvector. So maybe lambda 1 has 3 eigenvectors. What do you do then in this theorem? Well, pick any one of them. You could pick any of those three eigenvectors. This three is more, when I say three eigenvectors, I mean three non-zero linearly independent vectors that then the span is the set of all eigenvectors. So that's good. If you're talking about vector space of n dimensions, now you know that you cannot have more than n linearly independent vectors, because the dimension is n. That more than n linearly independent vectors would be a contradiction. Therefore, if you have an operator acting on a vector space of dimension n, since you cannot have more than n linearly independent eigenvectors, you cannot have more than n eigenvalues that are different. So if you have a set of eigenvalues, they give you a 3 by 3 matrix and list 4 different eigenvalues. That's not possible, because you would have to have 4 linearly independent vectors. So it's something that you learn. So it's worth trying to prove this theorem. So let me consider a proof. And it will be by contradiction. So we'll assume that these vectors, u1 up to un, are linearly dependent. u1, u2, and un are linearly dependent. Assume this. And we're going to try to see that we get in trouble with that assumption. So how are we going to get in trouble? So I'm going to be a little more explicit about this. For this, I will say the following. Consider these vectors, again ordered, u1, uk minus 1, uk up to un. I will say there exists a k with k less than or equal to n and k greater than 1, where the following happens. You see, this is the list of all the vectors. This is not, we're assuming it's not linearly independent. So look what happens. You say, you look at the first vector alone, and you say, is it linearly independent by itself? Sure it is. It's a non-zero vector. The second one, then you look, is it linearly independent? Well, you don't know. Maybe it already fails. That is, the second vector could be a multiple of the first, and then you're done. But well, suppose that doesn't happen. You go to the third and to the fourth, to the fifth. At some point, it has to happen that the next vector can be written as a combination of the previous ones. At some moment, it will fail. It may fail at the last step. They may all be linearly independent, but then, since we're assuming they're not, the last one may be expressible in terms of the previous ones, because somehow this list has to fail to be linearly independent. So however you order it, there will be, if you start with the first, the second, up to something, a set of vectors that are linearly independent. And then the next can be written as superposition of these vectors, where this k may be the last one, or maybe even the second one, although it's unlikely to be. So here is then our assumption. Our assumption that they're linearly dependent means that there's a subset of linearly independent vectors, and then the next one is not linearly dependent. So uk is in the span of these vectors. So what would that mean? And here, in the span of the previous vectors. And this has to happen. So UK would be equal to some number A1 times U1 plus up to some number AK minus 1, UK minus 1. That must happen. And remember, all these vectors are non-zero, so UK is non-zero. And this must happen, and some of the A's must be non-zero, because UK is non-zero. All right, so actually we've done most of the proof by now, even if it doesn't look like it, because what we do now is going to be simple. We're going to run into trouble very fast now. Apply T minus lambda K I to this equation. And see what happens. What is lambda k? Well, by our notation, is the eigenvalue of uk. Now, if you apply that operator to the left-hand side, it kills uk. That t of uk is precisely lambda ki. So you get 0. And then you get a1. And this operator, however, doesn't kill u1, because acting on u1, it gives you lambda 1 minus lambda k. And all the lambdas are different, and lambda k is different from 1. K is here. And then, I could write the second to make it more visible for you. You will be lambda 2 minus lambda k, u2, and then eventually up to ak minus 1, lambda k minus, lambda k minus 1. I'm sorry, lambda k minus 1 minus lambda k, uk minus 1. That's what we get. For each one, we get the corresponding lambda minus lambda k. So lambda 1 minus lambda k, lambda 2 minus lambda k, and finally lambda k minus 1 minus lambda k. And all these numbers are different from 0, are not equal 0. So these numbers are not equal 0. And now these vectors from u1 up to uk minus 1 are linearly independent. u1, u2, up to uk are linearly independent. These numbers are non-zero. Now, if you have a linearly independent set of vectors, the coefficients of them, a superposition of them, being set equal to 0 implies all the coefficients must be 0. Since these things are not 0, a1 equal a2 all the way to ak minus 1 must be 0 by linearly independence of the uk vectors. Up to uk minus 1, they were linearly independent. So being equal to 0, already we got our contradiction, because if all these are 0, you look back here, and the vector uk would be equal to 0, but we know all these are non-zero eigenvectors, so we got into contradiction, which means the hypothesis is false. The statement that they're linearly dependent is false, and that proves that the vectors are linearly independent. So let me complete here this all the k's equals 0 implies uk equals 0, and this is contradiction. And we've proven, therefore, this important theorem that associated to different eigenvalues, we have linearly independent eigenvectors. Now let's conclude with some discussion that is more along the lines of conventional treatments. This proof is a little unorthodox. This is not the way things are usually discussed. But now let's connect with the usual discussions. So we've said that the eigenvalue equation that was Tu equal lambda u could be written as T minus lambda I u equals 0, means this operator T minus lambda I is not invertible because it's not injective. And we proved not injective is not invertible in finite dimensions. So T minus lambda I is not invertible. Not invertible. So this means, in particular, and that's a result of linear algebra that we're not deriving here, that the determinant of this operator is 0. So determinant of T minus lambda I is equal to 0. So when an operator is not invertible, the determinant of it must be 0. And the determinant is something you calculate for a matrix. So if you want to calculate this determinant, you would typically choose a matrix representation of the operator and try to calculate its determinant. So if you did that, how would the computation look? It would look like you're computing the determinant of a big matrix that begins with T11 minus lambda T12 up to T1n, say, T21, T22 minus lambda up to T2n, and then you have Tn1 up to Tnn minus lambda. And this should be 0. The determinant of this matrix. This is the matrix in which you have the T matrix. So everywhere you see T11, T12, minus lambda times the identity. That puts a minus lambda at every element in the diagonal. Now this determinant, you can call it f, is a function of lambda. It's a polynomial function of lambda. If you see, the highest power of lambda that can appear here appears when in the determinant you're taking into account the contribution from the product of all the elements that lie in the diagonal. And therefore you get a minus lambda capital N times. So this begins like minus lambda to the n. And you can go on and on and on all the way down. So you could call it, let's see what is a good notation. Well, Bn minus 1, if you wish, times lambda n minus 1, all the way up to a number, which would be plus some b0. And not being invertible means that this thing is equal to 0. And therefore, you get an nth order equation, polynomial equation for lambda. And those will have solutions over the complex numbers. This is something you know. If you have a quadratic equation, lambda squared plus 1 equals 0, over the reals, you don't have solutions But over the complex numbers, you always have it. That's why we get a lot of eigenvalues when we solve over the complex numbers. Here you have plus minus I are the solutions. And here, if you have an nth order equation, there will be some solutions. What if all of this is 0? Well, lambda is equal to 0. It's a solution. It happens, it's like the polynomial lambda to the n. In any circumstances, there will be solutions. Many times, there will be n different solutions. That's the largest number of solutions you may have. But sometimes there will be repeated solutions. So this f of lambda can be written as minus 1 to the n, and maybe lambda minus lambda 1, lambda minus lambda 2, up to lambda minus lambda n. In fact, this is the general situation if you take into account the possibility that some lambdas may be the same. Because it may be that this whole polynomial is minus 1 times lambda minus 1 cubed for a 3 by 3 matrix. And then you would say, oh, this eigenvalue appears 3 times. So it's like lambda 1 is 1, lambda 2 is 1, and the last one, lambda 3 is 1. So in general, if it's an n, capital N by n matrix, you may have n different ones, but you may have that you have, for n equal 10, you may have 3 different ones, a few pairs, and maybe one that appears 3 times. Anything can happen. But the good thing is that you always have at least one eigenvalue, because this equation at least has one root. And it has just one root, for example, when all of these terms vanish and you have lambda to the n equals 0, then the only root is 0, for example. So a bit of terminology here. If the lambda 1s are different from lambda 2 are different from all of them are different, we say the spectrum is non-degenerate. If you find a factor in this polynomial, once you've factored it, you find that a factor appears with some power. So for example, if factor lambda minus lambda I appears to some power ki, where k is some integer that can be 1, 2, 3, 4, we say that this is a degenerate eigenvalue with multiplicity ki. It appears ki times. So it's degenerate eigenvalue. Then lambda I is degenerate with multiplicity ki. So these are the kinds of things that can happen. Now, if you have this situation and you find, so typically when you calculate things, the way it goes is that you try to calculate these eigenvalues first. This is generally the simplest thing to do, to solve this equation and find the eigenvalues. And then you say, well, how do I know that the eigenvectors exist? Then you say, don't worry. If the eigenvalue exists, this matrix, for that eigenvalue, this matrix has determinant 0. Therefore, it's not invertible. Therefore, it's not injective. Therefore, it kills some vector, and you're guaranteed you're going to find a vector for that eigenvalue. So, so this is the way you typically compute these things. And we will be interested in learning about the spectrum of operators. That will be a big task for us, in particular, operators that are special. And for those operators, we will need to be able to tell that they are special. We will need to introduce a little more structure on the complex vector space.